Hello everyone, I will present you the main results from the GRACE project about giant radio galaxies and their duty cycle. I am conducting this project at TINA FIAPS in Rome, together with Francesca Panessa and the Integral Group. Giant radio galaxies are among the largest single entities in the universe and lie at the end of the radio galaxy evolutionary track. The track starts with young radio sources like gigahertz sources, also called GPS, that present a size of about 1 kiloparsec or less, and a radio spectrum peaked in the gigahertz domain. This can evolve into classical Fanor-Riley 1 and 2 radio galaxies that constitute the bulk of the population, and eventually reach the extreme extension of about 1 megaparsec and thus become a giant radio galaxy, GRG. Once the central engine of these huge objects power off, it is possible to observe what we call a dying radio galaxy, where only the lobes are still visible while the radio core remains almost undetected. With a conventional threshold size of 0.7 megaparsec, GRG are not easy to discover in large radio surveys due to their low surface brightness and complex morphology. Indeed, only a fraction between 1 and 6% of radio galaxies in surveys like 3C are found to be GRG, with a total census of about 500 objects to date, thanks to the latest generation low-frequency surveys. It is still not clear whether the record size is due to a particularly favorable environment or high jet power or simply a long activity time. The first step of the project was the selection of radio galaxy from the high-energy AGN catalogs realized with Swift, BAT, and integral EBIS at energy larger than 20 keV. These provide the most extensive list of hard X-ray selected AGN in the sky, allowing to probe objects in a high accretion regime. In order to identify the radio counterpart, we then cross-correlated these catalogs with MBSS and SAMS radio surveys that together cover the entire sky in the frequency range 800 1400 megahertz and a similar resolution. We visually inspected almost 1,000 images, searching for extended structures and then measuring their linear size. We identified 67 radio galaxies with a double morphology, among which 31 are radio galaxies with a linear size larger than 0.5 megaparsec, and 15 are found to be giant radio galaxies, resulting in a fraction of 22%. This fraction is almost 4 times what we found for poorly radio-selected GRG, suggested that either an observational bias is at work or that the high accretion regime could play a role in the growth of radio galaxies. However, no correlation was found between the hard X-ray luminosity of the sample and the linear size. These first results were presented in Bassan et al. 2016. So triggered by this large fraction of GRG, we decided to better characterize the sample. In the first paper of the project, we show how this GRG present an X-ray EVS versus a radio core luminosity correlation consistent with what's expected from AGN with an efficient accretion. However, the log's radioluminosity is lower than what expected from the nuclear X-ray luminosity, suggesting that either a restarted activity made the nucleus brighter than in the past, or the lobes are dimmer due to expansion losses. This was the first paper from the GRACE project, published in 2018. From a radio point of view, many of these GRG result to be restarted radio sources from previous works in the literature, thanks to different indications that we can reassume as follows. A first clear indication of restarted radioactivity is a double-double morphology in which 2 pairs of lobes are visible, one external produced in a previous radio phase and one internal produced by a more recent reactivation of the core. In this image, for example, from the SAM survey, we can see one of the GRG from our sample that clearly shows such a morphology with the X-ray core position indicated by a cross right in the middle of the internal lobes. A second type of morphology that suggests a restarted radioactivity is the X-shaped one that you can see in the image here. Also in this case, two pairs of lobes are present, but the internal one has a different axis with respect to the external one. X-shaped radio sources can be explained at least with two scenarios. In the first one, this peculiar morphology originates from plasma backflowing from the lobes toward the core and then deflected by the host galaxy halo. In the second scenario, the new radio phase responsible for the internal pair of lobes is produced by a jet with a different axis with respect to the previous phase, thus suggesting a sharp jet reorientation. Obviously, only the latter scenario supposes a new radio phase. In some cases, the reorientation of the jet can be extreme, like this GRG from our sample, showing a blazar-like core at the center of a megaparsec scale structure. You can see from the MVSS image below that an emission gap is present between the core and the lobes, suggesting that the activity might have stopped for some kiloyear. A VRBI follow-up at parsec scale resolution revealed a one-sided jet, sign of a reorientation of the jet that is now closer to the line of sight. The broadband LCD modeling confirmed the blazar network for the core of this GRG, supporting the hypothesis of a jet reorientation of almost 90 degrees. Another morphology found among our sources and indicating more than one activity period is the radio cocoon one. As you can see below, this source displays a weak extended emission called cocoon, within which a compact edge brightened double-double source is embedded. In this case, the cocoon could be the remnant of a previous activity phase, while the current radio phase is inflating the lobes. Structures like this can only be unveiled by observations sensitive to large-scale, low-surface brightness emission, and also providing a sufficient detail to resolve the lobes and the inner region of the source. This can be accomplished with a combination of single-dish and interferometer observations, like this image, or with instruments like LOFAR, designed for this purpose. Finally, in some cases, a newborn radio phase can be spotted thanks to the presence of a gigahertz peak spectrum source, GPS, in the core of a GRG. As said before, GPS are young radio sources presenting a radio spectrum peak in the gigahertz range. Finding one of these at the center of a GRG formed during a mega-year timescale can be an indication that a new radio phase is ongoing, like the case of this source. Collecting information from the literature, we found that 6/15 GRG from our sample present signs of restarting radioactivity, so we decided to collect information for the remaining sources in order to check whether a similar scenario was present. We started a radio campaign involving both single-dish observations with the Effensberg telescope to check the presence of a GPS core and the GMRT interferometer to explore the megaparsec scale morphology of our sources. In addition to this, we made use of TGSS survey data released in 2017 and collected with the GMRT, plus images from the latest data release of the LOTS survey realized with the LOFAR interferometer. As a first result, we found that 8 sources harbor a GPS in their core, suggesting a restarting radio phase. This was the second paper from the GRACE project, published in 2019. Here you can see 2 GRG from our sample showing a GPS core. The one on the left shows also a diffuse of axis emission perpendicular to the jet axis. It is still not clear whether this is due to backflowing plasma or maybe a remnant from a previous activity. The one on the right shows a two-sided parsec scale structure for the core as unveiled from archival VLBA observation, confirming that the GPS spectrum is due to the mini lobes of the newborn radio phase. So summarizing, 6 sources out of 15 showed hints of restarting radioactivity from a previous work in the literature, while another 7 were found from our work. So in total, 13 over 15 GRG from our sample could host 2 different radio phases. These results were published in the 3rd paper of the project, published in 2020. So recently we got access to data from the LOTS survey realized by LOFAR at 150 megahertz at a resolution of 6 arcseconds. We could collect images for 5 GRG from the sample plus another 4 from the recent catalog update of a hard X-ray selected GRG from Bassani et al. For a total of 9 sources. In the left image, you can see one of the sources showing a GPS core. Thanks to lower sensitivity and resolution, it could be resolved in much more detail with respect to previous observations, confirming the presence of a diffuse off-axis emission region on both sides of the core. The southern lobe could also be resolved into hotspots, revealing a rich interaction with the intergalactic medium. The source on the right revealed a diffuse emission region called W2 on a different axis with respect to the one connecting the core and the western lobe, called W1. In addition to that, the inner jet shows an even different axis. So as a whole, the jet in the source could have underwent a counterclockwise reorientation along a mega-year timescale. This source is also found to be part of a galaxy cluster, which could play a role in the reorientation of the jet. Another source that you can see on the left revealed an X-shaped morphology thanks to the LOFAR sensitivity, with a pair of wings on a different axis with respect to the main lobes. The wings are more extended than lobes and present an enhanced emission on the edges, resembling what remains of a previous pair of lobes. This structure could be explained in terms of a jet precession as a result of a binary supermassive black hole or a precessing accretion disk. Alternatively, it could be the remnant of a previous radio phase with the jet on a different axis with respect to the more recent lobes. We could also perform a comparison of our hard X-ray selected GRG with the 239 radio selected ones from the LOTS survey, finding that on average, our sources are more extended than the radio selected GRG. The radio total powers at 144 megahertz are comparable for the two samples, suggesting that the hard X-ray selection should not affect it, despite the typically high accretion rates of our sources. So these results have just been submitted to MRAS and will be part of the 4th paper of the project. Thanks to the resolution and sensitivity of LOFAR, and in particular of the LOTS survey, we could unveil cases of diffuse remnant emission on the megaparsec scale, or in some cases, the presence of faint off-axis wings or a misaligned inner jet. For one source, a jet precession could probably be at work, and further high-resolution observation of the core could reveal the presence of a binary supermassive black hole. Finally, for another source, a jet reorientation due to cluster interactions could be present. Concluding, we define a sample of a hard X-ray selected GRG from integral and Swift catalogs, finding that the GRG fraction is 4 times larger among radio galaxies selected at high energies. The majority of our GRG presents signs of aerostatic radioactivity. While it is not clear yet whether a selection effect is at work, the sample is an interesting testbed to study the duty cycle of the radio phase in AGN. We are currently performing a similar study on a comparison sample of hard X-ray quiet radio galaxies to understand how the high accretion could play a role in the radio phase evolution. And in addition to this, we have collected EVN and LBA data on the whole sample of GRG plus the comparison ones to zoom into the parsec scale core of these objects, complemented by Merlin observations to cover the intermediate sub-kiloparsec scale. Finally, we are conducting pilot observation on 3 sources with GMRT and VLA to estimate the synchrotron aging of the different regions and study the radio duty cycle. If you want to know more about the GRIS project, you can have a look at our group's webpage, where you will find a page dedicated to these activities. Thank you very much.